Hello everyone. So we are now on the second part of the three-part series of unit operations review. Now for this part 2, we'll be discussing phase equilibria, gas absorption or stripping, then we'll have adsorption and liquid-liquid extraction or simply extraction. So for the first topic, that would be phase equilibria. The concept of phase equilibria is very important in all separation processes. Primarily, I say all because mass transfer will cease to occur when equilibrium between the phases have already been reached or has already been reached. So let's look into the concept of the phase equilibria. So as mentioned, mass transfer ceases when an equilibrium between the two phases is reached, and the rate of mass transfer is directly proportional to the driving force, which is a departure from equilibrium condition. Now, to be able to evaluate the rate of mass transfer, the driving force has to be accurately determined, which in turn rely on the equilibria between the phases. Now, nearly in all situations, just like as what I have mentioned, two phases are involved except in the case of two solid phases. The controlling variables are the intensive properties of temperature, pressure, and concentration. Now, equilibrium data can be shown or presented in the form of tables or graphs, and even can be represented in form of an equation. The relationship, that is, can be presented in the form of an equation. For most operations, however, the pertinent equilibrium relationships are mostly shown through graphs. Now, what are the bases for phase equilibrium? So, number one basis is the phase rule. So, in here, we determine the degrees of freedom or the variance, and it's just simply based on the formula that you are seeing. So it's the number of components present in a particular process minus the number of phases plus 2. Now the degrees of freedom or variance is the number of independent intensive variables. Now pressure, temperature, and concentration are examples that must be fixed to define the equilibrium state of the system. If you were done, the variance variables are fixed, an infinite number of states fits the assumption, while if f is too many, the system is said to be over-specified. Now for a two-phase system, variance is equal to 2, excuse me, which is also equal to the number of components. Now, if for example pressure is fixed, the liquid phase concentration can be changed independently. Then the gas phase composition and temperature in the case of liquid gas equilibria can be determined. So in this case, what was fixed is the pressure, and another given information which could be changed independently of pressure should also be given. In this case, it's mentioned that it's liquid phase concentration. Since we have already the two variables known, then we can determine what the problem requires. Like in this case, the one that is mentioned, it could be either the gas phase composition or the gas phase temperature. That's the essence of the degrees of freedom or variance. Now, as mentioned, so equilibrium relationships could be expressed in terms of equations, and it is also the basis for phase equilibria. Now, one such equation is Reynolds Law, and it is only applicable to what we call ideal systems or ideal solutions, which are said to be ideal because the way the components behave is similar. Now, in this particular formula of Reynolds Law, the partial pressure, the small p sub a, of component A is equal to the product of the pure vapor pressure of component A times the mole fraction of component A in the liquid phase. that's it. So partial pressure equated to the product of the pure vapor pressure and the mole fraction in the liquid phase. As to the pure vapor pressure of the component, you can get this in property tables. The next equation that could also express relationships of variables in equilibrium problems is Henry's law. So what is likable about Henry's law is it does not have any limitation. Whether the system is ideal or not, you can determine the partial pressure of component A in the gas phase by multiplying the Henry's constant H to the mole fraction of A in the liquid phase. So it's quite similar actually to the formula that was shown to you, expressing relationship also of partial pressure of A with mole fraction of A in the liquid phase. So everything here is defined. Now in the second formula here, so it says an OR is only a derived formula from the original or from the first. If we will divide this equation by the total pressure of the system, then the partial pressure on the left side divided by the total pressure will be equivalent to the mole fraction of component A in the gas phase. On the right side, if we divide Henry's constant by the total pressure, we will be producing as the quotient H prime, and we have still XA being multiplied to this H or H prime. And here you have already the exact needed relationship that we want, and that is YA in terms of XA. Now so far we have discussed three bases for equilibrium: the phase rule, the Reynolds law, and then we have the Henry's law. Both are equation in form. Now another one is the K factor, or what we call as the distribution coefficient. Now we use this particular constant in the topic liquid-liquid extraction. Now what does this represent? It's simply equal to the ratio of the mole fractions in the vapor and liquid phases respectively at equilibrium for a particular component. So you can see here mole fraction in the vapor over mole fraction in the liquid. Now if Reynolds law and Dalton's law apply, in the case of Dalton's law, it's just that saying that the total pressure of the system is equal to the sum of the individual partial pressures. So if this particular law holds, then our distribution coefficient, which is originally presented here in terms of the ratio of the concentrations of the gas phase and the liquid phase, will now be, or could be now determined using the pure vapor pressure of component I divided by the total pressure of your system. Now, if Reynolds law holds, we say, and this is very important, that the ratio of the K factors and the relative volatility of the components are the same. What do we mean by this? So the ratio of the K factor, so this is the K factor ratio. On top is in terms of component I, in the denominator in terms of component J, and relative volatility. So relative volatility could be in terms of ratio be equated to the ratio of the distribution coefficient K. Okay, this Y and this X came from the formula of the distribution coefficient. If K factors are strongly, or if K factors are to be assumed to be constant, it's quite okay, since we know that the change in the value of K for a change in temperature would only be minimal, as long as our system is only limited to a two-component system. So it's okay if we assume that K is constant, even though we fully know that K factor is strongly temperature dependent. But if again we only have two components in our system, then it's okay to assume that this K factor is independent of temperature. Now, this, by the way, K factor and distribution coefficient will be dealt with or again mentioned in the topic of liquid-liquid extraction. Now, so we have the last type of depicting relationships of variables at equilibrium. So this one is a sample, or these are samples rather, of equilibrium diagrams. The most common one is here in the bottom leftmost portion. So you have the mole fraction XA in the liquid to mole fraction YA in the vapor. We can have also Henry's law simplification of the curve behavior of the relationship between XA and P sub A. So what Henry's law does is, this curve is linearized and now we have this line to represent Henry's law. Actually, if you look very closely to Henry's law, it's really an equation of a line without any y-intercept, because you simply have y here being equal to mx. So we approximated the behavior of the curve into that of a line. That's Henry's law. Another diagram that could be used for phase equilibrium related problem is this diagram, which is able to give us the dew point and the bubble point at a given concentration for the liquid and for the vapor respectively. What does this mean? If you're given a liquid and you're given the mole fraction of A in the liquid, if you want to know the boiling point of that particular solution, you simply go up and stop on the saturated liquid curve. This is saturated liquid curve. One on top is saturated vapor curve, and one in the middle signifies a mixture of the two phases that was equilibrated. So if it's the boiling point temperature using XA, you can find it here. You just simply read it on the side. Now, if we have diagrams that could represent relationship of variables at equilibrium, we can also have tables. So in here we have temperature on the first two columns. We have here the column for the vapor pressure of benzene and toluene in a benzene-toluene system. And we have here the mole fraction of benzene in the liquid phase, that's for XA, and in the vapor phase, that is YA, for a process that is performed on a pressure of 1 atm or 101.325 kilopascal. So this table uses temperature. So if the problem gives you the temperature, all you have to do is read here the corresponding vapor pressure of the two components on the indicated temperature. Now, and in here you can also have their corresponding mole fraction. So in here it's solely for benzene. The mole fraction of benzene in the liquid phase and in the vapor space. Since we only have a two-component system, benzene and toluene, if this is the mole fraction of benzene, then if you subtract this from 1, that would be then now the mole fraction of toluene. Now this same principle should be applied in here. Now what is good about the table is you just need the temperature and you will have this information that you might be needing when you are solving problems. Now, as for the sample problems that I indicated here, they are not the same sample problems that I have discussed in class during the time of separation processes for you. So you just have to read this. That way, you will be refreshed on the things concerning phase equilibria. Okay, I have 4 sample problems for this. So I will stop here for phase equilibria, and we'll have a different lecture on recorded lecture on gas absorption and stripping.